All right, welcome to week 9 of AI504. And so prior to project 1, we mostly focused on like autoencoders and generative model, which are VAEs and GANs, and then CNNs, so which led to being able to write a code for GAN-based model, like a GAN-based model that can generate synthetic faces. So that was the gist of the first half of the semester, first half of this course. The second half, or actually a quarter of the next a quarter of the course would be focused on NLP, but NLP itself is it has a long history, so we can't go through all the NLPs. We're mostly going to focus on like the core discoveries made by the deep learning techniques in NLP. Like we're not going to touch upon like classical NLPs like NERs or part of speech tagging, parsing, none of that. It's just how we deal with NLP tech, how we deal with text, basically, how we deal with language using deep learning techniques. So we're going to start with word embedding, and then after that, we'll go to RNNs and seek-to-seek. And after that, it'll be transformers, then BERT and GPT. Then it'll kind of like wrap up the advances of deep learning NLP in the past how many years? Maybe like 8 years or so, because word embedding came out in 2013, if I remember correctly. So please focus very hard, very hard, and listen to what I say. If you're not familiar with NLP, like if this is the first time you are dealing with language or text, then it's time for you to pay attention. Okay, so word embedding. We're going to talk about word embedding. And I mean, it's going to be mostly word embedding. Document embedding is just a bonus. It's not really much of a thing these days. And then contextualized word embedding. So this will be very important. So contextualized word embedding is where the skipgram and the word to vec, and then after that came after like BERT and those kind things came out of, and then subword encoding, which is the foundation of modern NLP. Subword encoding, like when you do like BERT or GPT, they usually go through like byte pair encoding or word piece or sentence piece. That's what subword. That's where the subword encoding comes in. Okay, so word embedding. So what is a word embedding? So we usually, prior to like deep learning, like all the latent representation and vector representation, that's where deep learning really sparked its beginning. Before that, we usually turn to like a bit more classical or statistical method for representing stuff in a vector form. So for example, we want to express a word, any word, a boy, dog, cat, whatever, a word as a vector. And word is just, like if you think about a word in a dictionary, like English dictionary, there should be like about 50,000 words to 100,000 words. So each word has an index. Like the very first word would be like a something, and then the very last word would be like Z something, right? So we want to express that not as an index, but as a vector. So a cat, for example, if this is what we're after, then cat and a kitty are similar words, so they should have a similar vector representations. So cat and kitty, like they're like semantically they're similar. Morphologically, like their letters, their surface form are completely different. This start with C, this start with K, right? So they should have a very like different indices, but semantically they're similar. So they should have, when we want to represent cat and kitty as vectors, then those vectors should have a similar representation, meaning short distance, like short Euclidean distance, or maybe short in terms of like the cosine similarity, And hamburger is not similar at all with cat or kitty. So hamburger and cat, or hamburger and kitty, should have a very different vector representation. So far distance, Euclidean wise or cosine similarity wise. So the easiest way to encode any categorical or discrete variable into a vector form is to use a one-hot encoding, obviously. So for example, if you're trying to represent different blood types, A, B, and O, then obviously we could have a representation like this. So A, B, O. So the first, there are four variables, or actually like four blood types in total, like 1, 2, 3, 4. So we prepare a 4-dimensional vector, and then each dimension represents a specific type. So the first dimension represents A, second dimension represents B, third AB, fourth O, and only one out of 4 dimensions, only one can be 1 turned on, and the other has to be 0. It has to be like turned off. So that is why it's called one hot encoding, because only one dimension is hot and the other is cold. Right. So the problem is that if we use one hot encoding or one hot embedding to represent words, then clearly it doesn't capture the semantics. For example, if your dictionary consists of how many, like 20, like maybe 20 words, and you have horse and zebra in them, and you want to represent horse. So horse starts with H, and zebra starts with Z. So maybe they could be here and here. What happens now? So horse and a zebra, they are semantically similar, right? They're like all different types of horses, right? So the first one starts with H, the other one starts with Z. So syntactically, it doesn't have any similarity. It's the semantics that we want to capture. But the problem is, if we use one hot embedding, then no matter which word we try to pair up, their inner product will always be 0, because it's a one hot embedding, right? So they're one hot because it's an inner product. You guys know what inner product is, right? So if you multiply them and then sum them up, then it'll all be 0. So it doesn't matter if it's horse and zebra, horse and cat, horse and dog and person. It doesn't matter, because everything is one hot encoded. So their inner product similarity will always be 0. Euclidean distance will always be square root of 2. So that means that no matter which pair of words you find, their similarity or distance measure will always be the same. So it doesn't capture semantics at all, right? So that's the problem with one hot encoding. So we want something better. We want something a bit more sophisticated that can, for example, have vector representations that are similar for horse and zebra, but not similar for horse and desk, which was assumed to be very hard, because semantic, like injecting semantic into a vector representation, it doesn't, it's not very straightforward. If you try to think of a machine learning algorithm, or some kind of like learning algorithms, or like something like that, if you try to think about a learning algorithm that can incorporate semantics of words without human intervention, without human domain knowledge, how would we do it? It's not very simple. So that's why for a very long time, people usually just resorted to one hot embedding, or something called TF-IDF, which is actually not a word representation, but a document representation. So there was something called vectorization for document, or document vector, or doc vector, so which would be, so here we were trying to represent words as a vector representation, but here we're talking about pre-deep learning era method for representing documents as a vector. So for example, if your document 1 is like this, it's actually not a document, it's a sentence, but still, like, it's a very short document. So John likes movies, Mary likes too. Document 2 is John also likes football. So then clearly there are some similarities between these two documents, word-wise. Like there's John here, there's likes here, and also likes here as well. So there are like certain similarities. So how do we capture it using this word level statistics? So that's basically where we come up with word frequency, word document frequency matrix. So here, this axis is document axis. So there's document 1, document 2, and this is word axis, or term. We call it term axis. So we call this like term document frequency matrix. So in document 1, John occurs once. Document 2, John occurs once. Document 1, likes occurs twice, and document 2, likes occurs only once, and so on and so forth. So you have all the numbers, the value of frequency, the frequency of each word that occur in each document. So then this will be your document representation vector. So 1, 2, 3, 4, 5, 6, 7, 7-dimensional vector that can represent your vector. Obviously, I mean, we only use 7-dimensional vector here because the number of unique words in this entire document set, which only consists of 2 documents, is 7. So that is why we are able to use 7-dimensional vector to represent a document. But if we were to, collect many documents, for example, like all news from Naver website, whatever, then we will probably need much larger vocabulary that can incorporate that can include all English words probably. So maybe 50,000 dimensional vector or 100,000 dimensional vector. And each document will have a 50,000 or 100,000 dimensional vector where each dimension represents a frequency of the corresponding word in each document, right? So if you have that, then the good thing is that you can calculate similarity or distance between two documents, because this is vector 1, this is vector 2. And if you do a Euclidean distance, if you do like an inner product or cosine similarity or Euclidean distance, you can calculate them. And since similar documents who have like co-occurring words together, then their similarity will be higher. Their like inner product will be higher. Their cosine similarity will be smaller, or their Euclidean distance will be smaller, right? So that's what we did. Question: what is the loss function that forces this autoencoder to make words semantically abstract? Well, I'm not using any autoencoder here, so I don't understand your question. We didn't do any learning so far. One-hot embedding doesn't require any learning, any training. This doesn't require any training. You just count the number of words in each, count the number of terms in this document and this document, and that's it. We don't do any training. We don't. So if there's no training, there's no loss function involved. Does that answer your question? Okay, cool. So we haven't talked about any training procedure or any machine learning as elements at all so far. And so that was the simplest form of vector representation for documents. And a bit more sophisticated stuff comes afterwards, like TF-IDF, like term frequency, inverse document frequency. TF-IDF was like the kind of like the go-to method for representing documents a bit more in a more sophisticated way, rather than just simply counting. Because, for example, like he or she or the, like they would have a very high frequency in any document, which would not be able to distinguish between different documents, right? So you have like another mechanism called like inverse document frequency, but we won't talk about that here. So other vector representation methods, there are like matrix factorization methods. Like, for example, if you have it, again, the same term, a term document matrix, you could use singular value decomposition to, represent a document with a smaller size vector rather than like entire vector. And similar thing is something called like non-negative matrix NMF, non-negative matrix factorization. There is also probabilistic topping modeling, which was a big thing throughout maybe 2010 to 2015, maybe late 2000s to 2015, like right before deep learning. Like topping modeling was like a hot top, like one of the major research areas especially in NLP or text processing. So because it says like topic modeling, you want to find a latent topic. If you remember VAE, variational autoencoder, we talked about topping modeling as a form of variation, as an application for variational inference. We talked about how we collect news from labor websites, but we don't know the underlying topic, whether it's sports or celebrity or science or politics. So we can use like a variational inference for it. So that's where this thing comes in, probabilistic topping modeling. So there's something called latent Dirichlet allocation, LDA, that was like a very, very powerful method for estimating the latent topics with some well-designed generative process. But if you're interested, you can look it up later. I mean, they are no longer very heavily used, since now it's the era of deep learning, especially now it's GPT era. So nobody really doesn't care about topping modeling. All right, so word embedding. So now we're going to word embedding methods. So initially the people called, actually the inventor of word embedding, word2vec, or the inventor of like deep learning inspired word embedding algorithm, called it a distributed vector representation. I think also like the very old researchers call this like distributed vector representation, because as opposed to like one hot vector, which is like pointing, one hot embedding is a point estimate. Compared to that, if your vector has like 0.1, negative 0.5, 2.1, something like that, then your values are distributed over your entire vector. So this is called distributed vector representation. Anyway, so here, if your vector representation of words are distributed, continuous, basically continuous, then it's way easier to, it's way more easier to do like cosine similarity, Euclidean distance, as opposed to one-hot vector, because if you use one-hot vectors, then no matter which pair of words, it's always 0 for inner product, square root of 2 for Euclidean distance, right? So we're going to talk about 3 things. Actually, maybe skip on this one. Word2vec and glove. So Word2vec, it's a algorithm for training vector representations. So now we're talking about training. So training vector representation of word from context words. So context meaning in context is 문맥이잖아요. 문맥이니까 문맥이란 건 그 주변에 어떤 단어들이 위치를 하고 있냐인 거죠. So context words is basically adjacent words. Like what are your neighboring words. So the assumption is words in similar context will have similar meaning. This is the gist of Word2vec. So if some word occurs with another word very frequently, then they should have some kind of heavy correlation, right? So that would be the idea behind how to learn vector representation of words that can capture semantics, without injecting domain knowledge. We'll get to that. So for example, the cat purrs and cat hunts mice. So let's look at this one. So this is a one-hot representation. This is a distributed representation, and you can see that one-hot it's a very cute figure where you have clear cat for one-hot representation, a blurry cat for distributed representation. And you can see why this is, because if you change 30.2 to 30.4, 34.3, would that still be a cat? It's very hard to tell. Like which, in the one-hot representation vector, if this is 0 and this is 1, then this is definitely not a cat. This is something else, like it could be a dog or boy or car or truck, but definitely not a cat. So there's a clear distinction between one word and the other. But if you use distributed representation, then there is no longer clear distinction between one thing and another. Like if you add 1, it becomes 94.2. Is it a dog or is it still a cat? You can't really tell because everything is continuous, right? It's a spectrum. So that is why the author of this nice figure put a blurry cat here, which is very fitting, because no longer can we say something is definitely cat or not. It's just like a concept. It's it's like a latent concept, right? So hopefully this so far so clear, right? So the history of Word2vec or word2 vector, this notion has been around for quite some time, even before Word2vec. Like people try to use neural networks to learn a vector representation of words, but not so successfully until Word2vec. So there was like Kulober and Weston in 2008, Yoshio Benjo in 2003, even way back in 1986. This is like back propagation, so forget about this. But at least in 2003 and 2008, people try to learn a vector representation of words without putting any, domain knowledge. Like domain knowledge meaning like WordNet. WordNet has like all the hierarchies of word. Like I think, like person is a part of mammal is a part of animal, something like that. Like WordNet has that kind of hierarchy, but without using all of that, just purely based on statistics or like corpus, they tried to learn word representation, but it wasn't very like impressive. So Word2vec was the very first one that that on the surface, at least on the surface, showed that it captures semantics of words without any domain knowledge given, which is it's a very impressive feat of achievement. So what do we mean? So there's a bunch of things, but we can forget about this. What do I mean by a vector representations of words capturing semantics? So it's a vague notion, but here they have a very clear example that demonstrates Word2vec captures semantics of words. So for example, here, let's say that this is your origin. So this is two-dimensional space. It's like a Cartesian space. and this is X, and this is Y. And maybe I could, yeah, this is X, and this is Y, and this is Cartesian coordinate. And this is your origin, obviously. And let's say that after training your word2vec, however, we're going to talk about the training algorithm a little bit later. After training your algorithm, training your word2vec algorithm, your words will be represented as vectors. So let's, for example, say that you've trained your word2vec algorithm to generate two-dimensional vectors for each word. So king is here, which means that it's here. Men, the word men has a vector representation of 2 dimensions, so it would be here. Right? Because we're in a two-dimensional space. Woman would be here. It's a little bit, it's not a nice line, but you know. Uncle would be here, queen would be here. It's just something like that. So everything is just a vector, two-dimensional vector. But the interesting thing is not that men, where is it? Not that men and uncle and king, they're not clustered at all. They're like far apart from each other, right? And woman and queen, they're not also clustered from each other. They're not like, you know, in the vicinity. Like it's like far away from each other. But the important thing is the relationship between these words. They have a certain direction. So you can see that man to woman goes this way. Uncle to aunt goes this way. King to queen goes this way. So it means that the relationship between a male form and a female form, they have a like very similar direction. I mean, these vectors wouldn't be exactly the same. This would be like this, and this would be like this, but still, like they would have a very similar magnitude and also similar direction. So it means that somehow in this latent space, somehow in this two-dimensional space, the relationship between words are captured. And I mean, at the time, it was like a very phenomenal discovery. Like, because if you look, we're going to get to this, but the training algorithm of word2vec is extremely simple. It's not like it involves a lot of math or something. It's just very, very simple, intuitive algorithm. So people were like, you know, impressed, or like people are surprised that such a simple algorithm would give you a semantically induced semantically induced latent space. So once you know this, then you could do things like this. Like this was like a very popular example back then. Queen vector minus king vector plus, actually there should be a plus here. So queen negative king plus men would give you woman. Or actually this, let me see. King. Actually, let's do another example. This is not very intuitive. Queen minus woman plus men would give you what? Would give you king. So it's just, we're just, you know, shuffling the terms around. Like it goes here, this goes here, and this goes here. That's it. So, but if you look at this, I mean, end result is very impressive, which means that if you take the woman element out of the queen word, and then you add the man element, then what would that lead to? That would lead to the king. So very intuitive, very like linguistically intuitive. So this is why like word2vec was such a big hit back in 2013, 14, you know. And before BERT came out in 2018, people were still trying to use word2vec somehow. So it was around for like 4 or 5 years. Like word2vec was the go-to thing. Right. So this is just a couple of examples that what it can learn from the real data. So I guess this is, okay, yeah, this is a man and a woman. So brother, sister, nephew, niece, uncle, aunt, man, woman, sir, madam, heir, heiress, earl, countess, duke, duchess, you know, you can see where it's going. And you can always see that the vector, the magnitude and the direction of the vector, which is basically the relationship between the man and the male form and the female form, is always very similar. It's always like this, right? So you can see that something's going on. This is what is this? Is a company and a CEO. So Walmart CEO is some guy, Citigroup CEO some guy, IBM some guy, Viacom some guy. So it's like usually like this. And the next one is city and zip code. So Brooklyn 11226, Buffalo, whatever. So out of all the numbers, it means that this latent space knows that, like, if it was 11200, then the relationship between Brooklyn and that number would not be like this. It would be some other vector, right? So it means that this latent space, this two-dimensional latent space, knows that there's, for certain words, it has a clear connection with a certain city. So it's all like going like this. Right. Yeah, this was also another like nice example. Comparative is superlative. So slow, slower, slowest, short, shorter, shortest, strong, stronger, strongest. It's always between a normal form and a comparative form. It's this direction here. And from the comparative to superlative is always like longer like this. Question, is this graph the result from reducing the distributed vector into two dimensions? Yes, exactly. That is true. So I think in the early days of Word2Vec, people use like 100 dimensions for representing words. So you have 100 dimensional vector for each word, but you can't draw them. So you compress them into, I think they use PCA for this. So TSNE was probably not around back then. So I think the author of the paper reduced the dimension from 100 to 2 using PCA. Question, sorry for in the previous part of the class, 100 representations. Why use a 100 representation when the input size is huge? I think combination of ones and zeros without duplicating input values like in binary and simplicity. Actually, no, that is a good suggestion. So exactly like you said, if we use one hot embedding, then it is a humongous waste of space, because out of all dimensions, only one dimension will be hot and the other will be all zero. So you're just wasting the other like 99.99% of memory, just wasting it away all the time. So clearly we need a better representation. And as you said, as you said, we could use like binary form, like 1001100. You could do that, but even better is actually this what we're doing now. Even better, yeah, this, because it would be even more compact. I mean, binary representation is still like 10010 is still a waste of space, because for one dimension, you could only have two values, either 0 or 1. But here you can use any values, any continuous, any real values. But yeah, your suggestion is in the right direction. Right, and this not only works. So the great thing about Word2Vec is that it doesn't care. It doesn't depend on the language it is trained on. It also works very well on a lot of different languages, including Korean. So I'm not sure if this is still alive, but if you go here, if you go to this, if you if you go to this website, you could try things like this, like 한국 빼기 서울 plus Tokyo equals 일본. So it means that this latent space knows the relationship between a country and its capital city. So you can do things like this. So this is coming from a private blog from Wonjae Kim. Wonjae Kim is now a researcher in Naver. So this was his demo back in his, I don't know, 2015, like back when he was a grad student or maybe undergrad student. So shout out to him. So very interesting operations here. Barack Obama minus 미국 plus Russia will give you Vladimir Putin. So, nice. These are very nice. Like 아카라카 minus 연세대 plus 고려대 is 입실렌티, which is, back in 2014, this would be like, mind blowing. Now you can ask GPT to do this. Like ChatGPT will, like, you can give ChatGPT a few examples in the prompt. Like I want you to play this game, and then if you ask this, then it'll know what you're talking about. But back then, it was like phenomenal stuff. My favorite stuff here is this one. 소녀시대 빼기 소녀 plus 아줌마의 자유. So clearly, the citizens of Korea thinks that IU is a bit more older than 소녀시대. I don't know why, because as far as I know, IU is actually younger than 소녀시대. But this is but this entire thing was trained on like entire blog or what, Naver News or whatever. So it's it's like a collective intelligence. So it's collective intelligence said that this is true. So who knows? There was some other stuff like 최연석 셰프 minus 허세 plus 셰프 is 이연봉. Maybe some of you don't know 최연석 and 이연봉, so it's not very hilarious for you. Some of the stuff. Yeah, we can skip this now. But you can clearly you can see that this kind of relationship, this word-to-vec algorithm works on both English and Korean, actually a lot of different languages. Any language that has a sequence of words, then it will work. So the idea behind, so how do we do this? How did we, using a simple, what kind of algorithm did we use to capture the semantic in the latent space? So the core idea is that, as we said before, the words that occur in a similar context will have a similar meaning. Or in other words, you shall know a word by the company it keeps. So it means that it's all about the neighbor, all about the context. So suppose we read a word cat somewhere in any document. Suppose we observe a word cat. Then what is the probability of some word given cat that occurs that will read that'll read the word W nearby? So what is the probability that some word will occur in the vicinity of cat? So obviously, meow has a very high probability that it will occur in the same sentence or in the same paragraph, right? As opposed to potato. Potato and cat has no clear correlation. So there's no reason that potato and cat would occur in the same sentence or the same paragraph. Maybe fleas or pet, they have a higher chance, but Paris and baguette, probably not. So it's all about the conditional probability or the co-occurrence probability. Question: if there is no relation between existing vec and new vec, should you put in a new access? If there is no relation, exist between existing vec and new vec. I don't understand your question. Existing vec. Are you talking about this demonstration? All right, I guess that was a misguided question. All right, I'm gonna move on then. So there are two models in previous. Yeah, I still don't understand what you mean by existing vec and new vec. You mean like two different words or new axis? New axis meaning like new dimension? Yeah, you can wait. You can maybe follow the material and then see if you wanted to ask your question in a different form. All right. So there are two. The authors of Word2Vec paper suggested or proposed two different algorithms. One is called SIBO and the other is skipgram. So we're just going to go through the intuition behind each algorithm. So SIBO is that if you should be able to, given a context, you should be able to predict the center word. So there's like, I am a boy, dot, right? So I can write it down. I am a boy, dot, period. So if this is your sentence, then if we are already like, like if we can speak English in a proficient manner, then given the context, I am boy dot, given these contexts, you should be able to predict the center word A. So that is why this algorithm, SIBO algorithm, is convert each I am boy dot into a vector form. So this now is an I vector, M vector, boy vector, dot vector. You sum them up, you have a summed up vector, and based on this, you want to predict a vector. So that is the gist of SIBO. Skipgram is the other way around. Skipgram is that, so this is I am boy dot A. You can forget about cat here. Skipgram is the other way around. Skipgram is that given the center word, you should be able to predict its neighboring words. So given A vector, you want to predict I vector, M vector, boy vector, dot vector. So it's the other way around. So obviously this sounds more challenging. That's this one, right? But in reality, people use skipgram way more often because the skipgram captures all these things here, all these like like demonstrations here, it's all based on skipgram. So SIBO doesn't actually show this kind of behavior as clearly as skipgram. So in the end, people just started using skipgram only, and SIBO was like kind of got forgotten. So we'll take a look at this a bit more in detail. So how word-to-vec algorithm works. So you have, for example, you have a sequence of words. So well, I am a boy, you are a girl, something like that, right? So you have a sequence of words, and then there's always the center word and the neighboring words or the context words. So that we also call this like target and context, right? So if your window size is 3, you have to set the window size as a hyperparameter. Then this would be your context. If the window size is 2, then this will be your context. If the window size is 1, then this will be your context, right? Obviously. So as we said, skipgram predict the context words from center words. So if we're going to follow this example here, window size 3. So then what we do is, given the center word, you want to predict all the words in its context. So not the ones here, not the ones not here. So because if you use a too large window, then it would go out of context, right? So the very first word and the very last word in your sentence might not have a very high correlation or any like special relationship. So you want to keep the context window to a reasonable size. So maybe 5, or 3 to 5 is like a nice value. Why do you think skipgram is superior than the SIBO? Actually, that's a good question. Does anybody know the answer to it? This could be your quiz. Does anybody know why skipgram is superior than SIBO in terms of this kind of operations here? No, training. See, as I said, SIBO has a easier objective because it only predicts one word. But here in skipgram, you need to predict all the context words because we can learn more information. Work better than vector adding and subtracting. Yes, it's task is more challenging. That's a bit like vague. Predicted to multiple words. Yeah, okay. I would say that what was because it can learn more information. That's also a little vague. Yeah, I would say because skipgram is designed to predict the context. I think that's from Yijuyan. Skipgram is designed to predict the context. That's exactly. I would say that is as close as accurate as it gets because I don't think it's any. I'm not sure why people would assume that it has anything to do with infrequent words. But if you look at the objective function here, this is you are given a context and then you're predicting only one word. But here you're using a word to predict the context itself. So it's better at learning the context because it's designed to predict the context itself. So splits tokens per. And somebody said that it's easier to construct a loss function based on sentences, but it's same for SIBO. They're both are based on sentences. You just put in sentence and you calculate the context window size, and then you just construct a loss form. So both are just easy to construct. A lot of people say that this like skipgram has anything to do with infrequent words. Is that like common knowledge? Something that I wasn't aware of? No? Okay, I'm gonna move on then. Yeah, I was just wondering why so many people talked about infrequent words. All right, so it's a GPT answer. Actually, a lot of my question can be answered by GPT. Yeah. So I should think about something that cannot be answered by GPT then. Anyway, I'm not sure why GPT thinks that it has anything to do with skipgram has anything to do with infrequent words. Isn't that just simply because you have just one prediction per context? In SIBO, you only predict once using a context. In skipgram, you predict many times per context. Actually, no. Ngram is Ngram is what we call no, Ngram is something else. Ngram is completely something else. But Ngram is what? How can I say this? Ngram is a way to tokenize words. I think that would be most accurate. So Ngram is a way to tokenize text. Not tokenize words, tokenize sentences. So you tokenize your sentence by 2 words, that would be bigram. If you tokenize your sentences by 3 words, then that would be trigram. And based on that, you could do interesting stuff like language modeling. So exactly like GPT, you could build your language model using Ngram, which would be very, very primitive form. Anyway, so I'm gonna move on. So enough about the Ngram. Maybe we'll have some chance to talk about Ngrams maybe in the future. So how does word to vector? Oh, actually, how does skipgram work? It's right written in here. It's very simple. It's just 2 lines of codes, like 1, 2. So what's happening here is that this is just so the large T is like the size of the words in your text, maybe in your sentences. Like if you have like a 20-word sentence, then this could be 20. And this M is your context size or the window size. So if this is 3, then you would go from 3 here and 3 here. Like there's center word. So T is your entire like size of entire words, and M is your context window, and J is the index that you move around in your context. So given a context, so we can have like I am a boy dot. So this is your target. This is your target. Then, for example, here, like given, we can take a look at like this pair. Like this pair could be like right here. So given an A vector here, you want to predict M. You want to predict M. You want to maximize the probability or log likelihood of predicting M in your context, as opposed to all the other things that could be predicted. So this is the normalizing term, right? So how the concept of prediction here is just is realized as an inner product between 2 vectors, inner product between M vector and A vector. So remember that we are trying to learn a vector representation of all words. So you need to randomly initialize all word vector representations before you start your training, right? So M would be like everything would be like a 100-dimensional vector, for example, like some dimensional vector, and everything will be randomly initialized, and you're trying to learn their values. So that's the parameter that you're trying to estimate. And so what you would do is you take M vector here and A vector here, and you do an inner product between the two, and you want that to be larger than all the other vector inner product of inner product of pair of vectors that are not in the context. For example, here this is still A, but this could be dog, this could be car, this could be, I don't know, like truck, cat, whatever, all words in your English vocabulary, English dictionary, all words. So this is all words, W. So this could be like 50,000 or 100,000, depending on how large of a dictionary you use. So this is where the bottleneck is actually, because every single time you try to like, learn a log likelihood, maximize the log likelihood of A boy, A M, A I, A dot, you always have to go through this. Actually, sorry, no, not this is fixed, so you can reuse it. But if you move to the next word, when this becomes a target, then you need to do this. You need to do this for the boy in here all over again, and then when you move to target here, then again, like, so this would be the bottleneck term. So yeah, very like it's extremely easy, right? So, and before in the old days, I'm not sure if this is still a thing, but in the old days, people used different sets of vectors for when this is the so for example, let's say that at some point this will be the target, right? So when this is the target, boy is a context, but when this is the target, A is a context. So some people, well, actually the original authors of Word2Vec used different sets of vectors for target vectors and context vectors. So like two sets of lookup embeddings, basically, two sets of parameters to estimate. So the thought was that a word that operates as a target and a word that operates as a context should have different semantics. So that was the idea behind it. But in my experience, it doesn't really matter. So this is where, so input vector, output vector, meaning this is the vector for target, this is the vector for context, and sometimes they don't have this exactly the same semantics like here. I mean, sorry, here, they have different semantics, here, different semantics, here, different semantics. But in my opinion, it doesn't, I don't think, and first of all, nobody really uses Word2Vec anymore. And, you know, implementation wise, it's up to it, you can use your imagination. Right, and the softmax implementation are so this is what I was talking about when we do this here. Here, you have to sum the vector inner product across all words from word A to word Z, right? So this is the bottleneck. So softmax implementation is slow, so that's what it's talking about. So there are two methods to overcome it. One is hierarchical softmax. Well, I won't go into detail. This is just basically building a binary tree to, calculate the softmax in a bit more efficient manner. But people just use negative sampling, which is that instead of summing through all the words in your dictionary, you just randomly sample like 10 words or 5 words, and then you're just done with it. So that's what negative sampling is, because you sample like maybe 10 or 5 words that would act as a negative pair. This is the positive pair. This is a negative pair, right? Like when you're doing contrast learning. So you would randomly sample negative pairs, like maybe 5 pairs or 10 pairs from your dictionary. So and that actually works pretty well. So people call it negative sampling. Yeah, the K is the number of samples being extracted. So K equals 5 or K equals 10. People usually use K. I think people used to use K equal 5. And it's a sampling. So obviously, you need to run it many more times to make it really accurate, as accurate as when you're using the entire samples, but nobody has the kind of time. Right, so after you learn Word2Vec, where do you use it? So after you learn Word2Vec, you would have a vector representations for all words in your English, in your English dictionary. From A to Z, you have vector for A, vector for cat, vector for boy, vector for car, truck, dog, whatever, right? So and they're all learned, they're like fixed, right? So once you have, actually there was a question. Maybe because let's say a word center is happy and other word is with similar meanings. So I guess C is more likely to give happy as output because it's more common than euphoria, but skip will work well with both. Oh, I see. Okay. I mean, yeah, that could be another interpretation. Right. Maybe I'll need to think about it. So, okay, moving on to application of Word2Vec. So as I said, once you finish Word2Vec, you would have a fixed set of word vectors. So where do you use it? So first of all, you can use it for word similarity. So word similarity, because word representation that you learn from Word2Vec, they are continuous representations, so they're semantically informed, they're semantically like injected, so you can use them to see if dog is similar to cat as opposed to dog is similar to truck, or actually no, dog and puppy and dog to truck. Then you can calculate this inner product or the Euclidean distance or the cosine similarity to see which one is similar to which one. You can also use as a word lookup embedding, like you can load the lookup embedding for word like machine translation. So for example, when you do machine translation, for example, here you have a encoder and a decoder, right? We'll get to this. Maybe I think we're going to get to this next week. But as a preview, when you're doing, for example, English to I am a boy to je suis something. I forgot the French. Anyway, so you put I am a boy into the encoder, and actually no. Right here, because it's a decoder, it should go out, right? It's coming in, it's going out. When you do this, you need to have a lookup embedding that you can put you need to convert I into a vector and then put it into an RNN or transform or CNN, whichever model you want. You need to convert M to a vector and then put it into encoder and so on and so forth. So if you don't use continuous representation, then you would convert I into a one hot vector, and then put it in. Then you would hope that something would change, something would happen inside the encoder. But instead of doing that, you can use word2vec to convert I into a bit more semantically informed representation, the word2vec representation. Same for M. You can convert M to a word2vec M and then use it to put it into an encoder. So that would give you a bit more better performance when you're doing machine translation, part of speech tagging, name identification, sentiments, yada, yada, yada. So it doesn't always drastically improve the performance of your application, but sometimes it does, sometimes it doesn't, you know. But sentiment analysis, this kind of thing would work very well because sentiment analysis is all about like the semantics of the words. But I'm not sure how much word2vec will improve the performance for machine translation. But people used to do this a lot up until like 2017, 18, like early 18, before BERT came out. Like people used to still initialize their word embeddings using word2vec or some other like word2vec variants. Glove is another way to learn word representation vectors. So this is another word embedding algorithm. So as opposed to word2vec, which is very local because you only look at one context window at a time, right? You only look at one context window at a time. So given this context, what you would do is you have 1, 2, 3, 4, 5, 6 prediction functions basically. But so that would be it for this window, and then you slide to the next window, and you do the same thing, and then you slide to the next, and you do the same thing. Slide to the next, and you do the same thing. It's just so you just keep sliding to the next context, and that is why I say that the word2vec algorithm is very local. But as opposed to this, Glove is actually a bit more Glove is global. It has global in the word in the title as well, because you actually first compute the co-occurrence matrix. Co-occurrence matrix meaning the term document frequency matrix. So you have all the documents here: doc1, doc2, doc3, doc4, and all the words like word1, word2, word3, word4. So there will be like numbers like 1, 5, 0, 3, 2, 2, 0, 0, something like that. Right? And using this matrix, you would run this algorithm, which is a bit more informed which is a bit more sophisticated than word2vec or skipgram, because it's more like it's trying to learn the vector representation, the UI and UJ, the vector representations based on the global statistics, not the local statistics. So it trains faster, obviously, because you only need to look at this term document matrix. You don't have to slide your context every single time, so it's way faster. And works well with even small corpus, or so people says. But I don't think people use Glove that as often as word like skipgram, because Glove doesn't give you this like nice king minus queen plus like men plus women. Like it doesn't work that well in Glove. And the doc2vec. So doc2vec is another extension of word2vec, or some people call it paragraph2vec. So basically, when you're doing skipgram here, when you're doing I guess they do it like this, like a SIBO version, skipgram version. But here in skipgram version, what you would do is you have a vector representation for paragraph, or document set aside. So in addition to all the word vectors in your word English dictionary, you have like document IDs that become a word vector, and then you try to train their word vector using like this kind of a skipgram type of context window prediction. So then your document your paragraph vector would be informed of its context, which is basically all the words that occur inside the paragraph. Then you can use that paragraph to do something like paragraph similarity prediction, that kind of stuff, or document classification, clustering, and that kind of stuff. Right. So this is the word embedding. So word embedding and word2vec and glove and doc2vec. So any questions so far? So I'm not sure if people these days, or researchers these days, care that much about word embedding, because word embedding is just a step that you take to tokenize words and then put into GPT, like using byte pair encoding. So it no longer has that much of a it doesn't garner that much interest. Like what kind of embedding, like what kind of information each embedding encapsulates, like how it operates inside the latent space. Like people don't really care about that anymore, because people it's all about generative model these days. And what kind of latent embedding or what kind of embedding is learned through the generative process, it's not very straightforward, actually. Does doc2vec require larger hidden dimension than word2vec? Actually, no. Interestingly, all the words and document vectors, they're the same size. Otherwise, you wouldn't be able to do this kind of operation. So if this is 200, this is 200, which is a bit counterintuitive. All right, moving on. So if there are no more questions, moving on to the subword encoding, which is the foundation of modern deep learning now, because everybody uses subword encoding. So subword encoding, words in writing systems. So words in writing, they vary very much by different languages and different writing styles. Like some language doesn't even have. So far, what we've done is we looked at word embedding, but word embedding assumes that your language operates on words, right? So your text can be broken down into words, word level. But in here, look at this. There is no. You need to first segment this into word level, but it's not very straightforward, And sometimes it's like the words the language would be like compositional, like you add these to get this. So this becomes a single word, but semantically it has many meanings. And so in that case, it's very hard to operate based on words, because word is very Latin based. Maybe not. I'm not sure if I can say this, but it's very like Western concept. Like your text, the smallest unit of text becoming a word is kind of like very convenient for Western style, but probably not for like this or like even this. So the concept of word2vec kind of doesn't generalize well to other languages. So we need something else. Like if you want to learn a embedding if you need like a unit embedding to process language or text, you need something better, more generalizable than words. So that's where subword encoding comes in. Oh, and other motivation is that some words, even if you can operate on words, in some languages, like a single word is like really long and compositional. So, for example, here, if this is, what is this? This is Polish or Hungarian, or I'm not really sure. But like German words are like this. Like German words, they compound they concatenate all the meanings into a single word. So the single word becomes really long. But in essence, you can break them down into multiple subwords, subparts. So that's another motivation. Like sometimes your words are too long, or transliteration. Christoph, this also can happen. And in the era of Twitter, like everybody like misuses words, or makes plays around with the word, like good or vibes, or like I don't know, I don't care. I'm like something for you. Like, so like these don't conform to the classical words that you find in the English dictionary. So you need a much more robust ways to break down your sentence into a bit more, like unit form, unit level. That is not word. That is a bit more granular than words, because like you can't handle this with words. So there comes. So before like subword encoding, people try to use character level models, obviously. So if you can break down everything into just single letters like W, H, E, N, I, D, C, then you no longer need to care about what is a word and what is not a word. You just care about the letters. So if you can just learn the letter embedding, character embedding, so it becomes a character embedding, not a word embedding, but character embedding. If you can, then you just need to learn like 56 characters or something, like all the ASCII characters, like the small lowercase English, uppercase English, the hyphen, the question mark, and the exclamation mark. You just need to learn maybe 100 characters at most, right? Maybe 100 character embeddings at most, and then you can use them to process any like Twitter or whatever. So that was the idea behind character level models, and it did work pretty well actually. It had like promising purely character level like machine translation model. Actually worked pretty well by like 2016. Not very well in 2013, but maybe like by the time 2016, character level NMT models worked pretty well. So let's see. Yeah, both models. Yeah, actually, yeah, these. Yeah, we can skip these. These two are the same. So 2016. Yeah, I guess we can. So can you so if this does this solve all the problems? So for example, if we are using character level models or character level NMT or character level generative model, whatever, character level whatever, like document classification, sentiment analysis, does breaking down your text into character level model solve all the problem that we've talked about? Can you think about any downside of breaking down your text into character levels? It's a question. Are there any downsides? Or does this solve all the problems? Can you just forget about words and just operate on letter level or character level? Require too large dictionary? Actually, it's the other way around, because as I said, you only need to learn 100 character level embeddings as opposed to word, because word is a combination of letters. So you only need, in alphabet, you have like 26 letters, right? So you don't need large dictionary. Many combinations. No, it's not the context actually. Context is like a byproduct. It's yeah, some people say that so many computations, it's the computations. It's the computations. Because if you think about breaking down breaking down your text into words, this is only 2 words. So you need to put them into transformer, like the input to the transformer or RNN or whatever would be 2, a sequence of 2 tokens. But if you break them down into characters, it's like how many? It's like 20 or 30, like 20 or 30. It's a sequence of 20 or 30 tokens into your RNN or transformer. So it's the computation that's the bottleneck. Breaking down your text into character solves a lot of problem, except for that it just requires too long context window to consume all the characters inside your text. So that's the problem. So sooner or later, people just try to move on from character level to something more clever than character level or word level. Yeah, it's not, yeah, it's computation. Yeah. Some people just said that very early on, but yeah. Loss of meaning, loss of too many combinations between combination vectors that, yeah, those are not the main reason. Those are not like the biggest downside. It's how many times you need to run a for loop to actually congest this in a letter level. Actually, there is here. Yeah, it was very slow. So So back in 2015, English Czech machine translation contest took 3 weeks to train. So, but the performance is not that bad. Like word level model is 15.7, character level model is 15.9. It's actually even better than word level, like only by 0.2, but still like comparable. But it's the time that really is a model that becomes a barrier. So there were some more informed, like more sophisticated design for character level NMT, and it showed great performance, But well, yeah, we can skip this. This is based on CNN actually. Like here's like CNN. Right, so now the subword model. So we go into now subword encoding. So just as I said, word level embedding cannot generalize well to other languages, or even like misuse of language in like Twitter, or like typos, or like puns or abbreviations. Doesn't generalize well. And character level models just takes too long time to do anything, right? So byte pair encoding came around in when? It's like 2016, I think. Yeah, 2016. So very, very like, very, I don't think anybody remembers where this came from now, but it was a very like, it's the foundation of modern like deep learning and NLP deep learning. So byte pair encoding actually comes from a compression algorithm. So when you do like signal processing, you send signal from one signal to the other place, and you want to compress the signal so that you don't consume too much bandwidth and that kind of stuff. So it comes from that, but you can directly apply it to the language, because language is also a signal. It's a signal based on discrete tokens, right? So most originally, if you're familiar with byte pair encoding from the compression algorithm, you can just simply think about both compressing most frequent byte pair into a new byte into a frequent replace bytes with character engrams. So instead of replacing most frequent byte pair to a new byte, you change the most frequent character pair to a new character. That's it. If you're already familiar with byte pair encoding. So we can look at the example here. This is a very nice step-by-step example. So first, what you do is, for example, let's say that you have, let's say that you collected a bunch of documents, and then throughout the documents, you calculated the number of words that occur in the entire document set. So low occurs 5 times. Lower occurs 2 times, newest occurs 6 times, widest occurs 3 times in your entire document, in your corpus, right? So given that, what you do is you first start with all the letter level vocabulary. So L, O, W, E, R, N, E, S, T, Y, W, something like that, So you start with all characters in vocab. So you start with one letter, like one letter. And then what you do is you calculate, you start putting pairs into, like you start with LO, OW, EWE, ER, RN. Like you keep looking at a pair of letters, and see which one's the most frequent. And out of all the pair of letters, out of all the letter pairs, character pairs, ES happens to occur 9 times. Out of, like, for example, LO occurs how many times? LO occurs 7 times. OW occurs 7 times. What else? Yeah, I don't see anything else. But for example, but ES occurs 9 times. So that's why ES becomes the new word, new entry to your vocabulary, right? It wasn't there here. But since you started calculating, counting how many pair of letters occur inside your entire dictionary, the largest one becomes a new entry to your vocabulary. And you keep doing this. Next one is EST. So you see that ES is now a legitimate entry to the vocabulary. Now you start seeing LO, like OS, and DES, or TES, SS, SES. Like everything becomes like a candidate pair. But out of all the candidate pairs, EST, which is a combination of ES and T, is the largest because it occurs 9 times. Again, like as opposed to LO 7 times, OW 7 times. Out of all that, ES plus T occurs 9 times. So now EST becomes a legitimate a new entry to the vocabulary. W? Oh, you mean like W and WE? W, it only occurs like 8 times, so it's not 9 times. So it's not there. We're not there yet. We're still working on the 9 times level. Right. After that, it becomes actually it should have been WE, but I guess the authors of this figure made a mistake because WE should have. Where's WE? Oh, actually, yeah, W doesn't work because now it's either WEST. It's no longer WE and WEs because now it becomes a single entry. So now it's WEST. So you can't go to WE 8 times. It's now LO 7 times. So now LO becomes a new entry to the vocabulary. Do we have to be careful with the sequence in the pair? Sequence in the pair? Actually, no, because you said as I said that ES and T became EST. So T came after ES, so it doesn't matter. Why does EST appear 9 times, not 2 times? I'm not sure. EST, like ES and T 9 times. Okay, so hopefully. Okay, I'm gonna assume that was answered. Yeah, ES. Okay, so then it becomes LO. So now L and O, LO 7 times. So LO 7 times. That becomes LO, and so on and so forth. You keep doing this. You keep doing this until when? Until you are satisfied with the size of your dictionary or size of the vocabulary. So now the size of the vocabulary, it doesn't depend on the size of the corpus or anything. It depends on your preference. Like I want to build a vocabulary of 10,000 or 20,000 or 40,000. Doesn't matter. It's up to you. So you set how large your vocabulary, you set how large you want the vocabulary to be. So it's a little bit of different paradigm. Right. So yeah, so it automatically, so good thing is it automatically decides vocab for a system. So what you do is, let's say that you want to provide a machine translation service between English and Korean. Then you need to have a vocab for English and Korean. Prior to this kind of byte pair encoding, what you would do is you would look at you would depend on domain knowledge, basically. You would get a English dictionary, Korean dictionary, and then you start counting like how many you can digest, and then you either use them or like filter some kind of stop words, that kind of stuff. But here what you do is you just simply collect all the documents in English, all the documents in Korean, and then you start building this byte pair encoding by running this algorithm on one corpus and another corpus. So it's a automatic decision. It's automatically decides the vocab for a system. So it's more like it's statistically motivated. You no longer care about whether a dog is in your vocab, whether a cat is in your vocab, whether like long words such as like elementary or like circumlocution. Like you don't care what kind of words go into your vocab. You simply run this algorithm until you're satisfied with the size of vocab, and then it would give you the most like statistically informed vocab set. So you don't need. So it slowly this domain knowledge, like linguistic knowledge, is no longer needed, because even for deciding the vocab, you just run a algorithm without knowing anything about the target language. You don't need to be fluent in Korean to construct a byte pair encoding Korean vocab. You just run an algorithm and that's it, right? So it's kind of like widening it's lowering the entrance hurdle for NLP. So there's something else called word piece and sentence piece, which is basically the same thing as byte pair encoding, but it uses a bit more sophisticated loss function. So here, rather than counting n-gram and then greedily selecting the most frequent pairs, this was a greedy algorithm, right? You start with ES 9 times, 7 times. So it's a greedy algorithm. But as opposed to that, what word piece or sentence piece does is that out of all the candidates, you select the one that maximizes the language model likelihood or reduces perplexity. So that the candidate that reduces the information entropy the most. Like you want to select the ones that minimizes the entropy the most. So that's a bit more like sophisticated than simply going greedy. Question. I have question. Vibes in vibe will be recognized as 2 words in this hour. No, actually, no. We don't know. We don't know. It all depends on what is inside your vocabulary. So vibes is vibe and vibe. Vibe. Okay, Apple Pencil low. Fortunately, we only have a few more slides to go. Vibe. So probably vibe will be in the vocabulary. Vibe it will be in, if you're building a vocabulary like 30,000, then vibe will definitely be in, like very likely that vibe will be inside the vocabulary. So vibe will, this will be its just own token, but vibes will be probably, it'll be broken down into vibe and then maybe SS, because sometimes people use S, like glass has SS maybe, so SS will be a thing in the vocabulary, and maybe ES will be also a thing in the vocabulary, and then just E. So that's it's just my imagination, but it depends on what's inside your vocabulary. So it'll always go for the longest subword first, which is vibe in this case, and then after that it will be the next longest subword and next longest subword. So it'll give you in my estimation, it'll be broken down into vibe, E, ES, and SS. Does it make sense? Okay, cool. Right, and then we were talking about word piece and sentence piece using different objective for selecting the most probable word, or the word that minimizes the perplexity or maximally reduces perplexity. Sentence piece is a little bit different. Sentence piece actually embraces white space as another token, so that it doesn't even care about the white spaces, because in byte pair encoding we at least had to go from here, like we had to at least break down all the text into word and then count the word frequency. But in sentence piece, even a white space becomes a token. So now it's like completely you just don't care anything about the structure of the sentence, like whether there's like a white space or not, you just don't care. So the important thing about word piece and sentence piece or byte pairing, actually, BERT uses word piece or variant of word piece. So you should be familiar with this subword encoding concept. And GPT uses, I think GPT uses byte pairing encoding, BPE. So that means that it doesn't really matter whether you use word piece, sentence piece, byte pairing encoding. Doesn't really matter which one you use. It's as long as you have like a good starting point for tokenizing words, then the rest will be taken care of by dozens of layers of transformer, because in the end, the transformer will take care of all the context windows, all the neighboring words and the relationship between neighboring words using attention mechanisms. So in the end, it depends on the size of the model and the power of the model. But at least you want to have a good starting point using word piece, sentence piece, or byte pair encoding. Right. So yeah, very last stuff. So the very last stuff is embedding contextualized word embedding, contextualized embedding. So this is where BERT, actually Elmo and BERT came out of. We'll get to this actually 2 weeks later. So for example, here, there was a model called Elmo, which was the first work to do contextualized word embedding. So contextualized word embedding versus word2vec. So word2vec is a static word embedding. Once you train word2vec, you have a not fixed word lookup table that you can convert your word to a vector representation. That's it. So it's fixed. But what we want to do is something even better than that. So here, this is the motivation. So here, this user asks Elmo, the word embedding model, give me an embedding for the word stick. Then the Elmo says, appropriately, there are multiple possible embeddings, meaning that a stick can have multiple meanings. It could be a stick, like a wooden stick, or a stick that you stick to like a wall using a sticker. Like there could be different meaning. There are a lot of different meanings in a stick. So there can be multiple possible embeddings. So you need to use it in a sentence. give me an example where you use the word stick, then I'll give you the proper stick embedding. So here, this guy says, okay, let's stick to improvisation in this skit. So in the word stick here is used as a, sticking to the original plan, right? So in this case, the embedding is this. So here, this Elmo is way more sophisticated, way more linguistically intelligent than word2vec, because word2vec can only capture one meaning at a time because it's fixed. But here, if the model can accept an example sentence where the word is used in a sentence here like this, then it can give back a more appropriate, more informed embedding for this particular word stick. So that's where Elmo comes in. That's where BERT comes in. That's where GPT-1 came in, actually. So we'll talk about that 2 weeks later. Right, this is the basic architecture. So Elmo has like RNN going forward, RNN going backward. This is BERT using transformer going both ways. This is GPT using transformer going only one way. And this was all based on this intuition. I want to have a better word embedding that can take in the context and then give back a more informed vector embeddings. But then GPT went whole the other way, went to GPT-2 and 3 and then ChatGPT. So that's another history. All right, so I think this is it for today. Any question before we end the class today about word embedding? So word embedding is no longer like a hot topic anymore, but it was where all this like BERT, GPT, and Elmo came out. So it's very important that you know the history, and then sooner or later you'll like there will be an opportunity where you can actually use this knowledge. This Thursday, you'll be able to practice word2vec, how to train word2vec, and then do that linear operation, king minus queen, that kind of stuff, and play around. All right, if there are no more questions, I'll see you guys next Tuesday then. All right, thanks. Bye-bye. All right, thank you. Bye-bye. 네, 감사합니다. 네.